Welcome back. Today we'll do section 1.4 on divisors. Alright, as always in math, let's start out with the definition. Definition. For integers a, b, and eventually p, we'll first of all say that a divides b if the following. It's written, let's see, a divides b with the vertical slash. And we assume a is non-zero, of course. And maybe the first time you see this, you should think of it with the words evenly. It divides evenly. So a divides b evenly if b is equal to a multiple of a. So that just means b is a times k. Number 2 is the definition of primeness. We exclude 0 and plus or minus 1 here, so that we say p is prime if and only if its only divisors are plus or minus 1 plus or minus p. We exclude 0 because it's not really so useful when you're factoring things, and plus or minus 1 are excluded mostly just for a technicality. They certainly satisfy the property that their only divisors are themselves and plus or minus 1, but they'll mess up our unique factorization eventually. So we'll shortly prove that 6 can be written as a product of primes uniquely, so that'd be 2 times 3. But if you counted 1 as a prime, you could also write it as 2 times 3 times 1, and you'd lose the uniqueness, or 2 times 3 times 1 times 1. So in general, later on, anything like plus or minus 1 in more abstract settings will have to be excluded from notions of primeness. All right, quick examples. 2 divides 10. That's because you can write 10 as 2 times 5. But 2 does not divide 11, because 11 is not a multiple of 2. Similarly, 2 is prime, and 4 is not. All right. Our first lemma is just a bunch of properties about what it means to divide one number into another. They're all completely straightforward. I think we'll only prove one of them. But here's the theorem, or maybe lemma would be better. The first statement is that 1 divides anything. That's pretty clear. The second statement is a type of transitivity. So if a divides b, and in turn b divides c, I guess you need b not equal to 0 here, then the conclusion is that a also divides b. Number 3. If a divides b and a divides c, then a will divide any linear combination. Namely, if x and y are any other integers, a divides bx plus cy. Number 4. So if a divides b, at least for b non-zero, then you get that essentially a has to be smaller than b. The precise statement needs absolute value signs, but anyway, you get that the absolute value of a is actually smaller than the absolute value of b. There's a corollary of this that I'll stick under here that's worth noting for our next definition. For b not equal to 0, the set of divisors of b is finite, and that follows just immediately for number 4 there. And finally, number 5 of the lemma. If a divides b and b divides a, technically you need b not equal to 0 here, then that's because a and b are the same up to minus 1. All right, so for the proof of the lemma, let's just prove, say, number 3, and the rest we'll leave as exercises in the homework. So the setup is that we have a dividing b and a dividing c. And we want to show that we get that A will divide any linear combinations. So this is just, of course, a definition chase. What does it mean for A to divide B? It means that you can write B as a multiple of A. And of course, A divides C just means that you can write C as a multiple of A as well. So now you can just multiply this equation by x and this equation by y and add them together, and you'll get the result. So bx plus cy is a multiple of a, and that implies that a is a divisor of bx plus cy. So that's the proof of 3, and the rest of them are all very similar. All right, and that's all we'll do. All right, next comes the definition of the greatest common divisor, which plays a huge role in a lot of math after this. So here's the definition. The setup is to start with any two integers. They can't both be 0. 1, 0 is fine. The first definition, we start out with a non-zero integer c. If it divides A and it divides B, then it's called a common divisor of A and B. All right, and number 2, these definitions almost define themselves. Just says the largest common denominator. We ought to call it the largest common denominator, but instead we'll call it the greatest. So there we have it. The greatest common divisor is just the biggest of them, and we have a special notation for it. It's written with parentheses. So that's the notation. If you put parentheses around two integers like that, then you're talking about the greatest common divisor. Finally, number 3, the notion of relatively prime. When two integers have no real divisors in common other than 1, and, well, minus 1, then we say they're relatively prime. All right, I guess definition number 2 requires a small note to give existence. The first is that there are always common divisors, namely 1 is always a common divisor. And then the next comment is that the set of common divisors, which is now non-empty, we see, is also bounded because at least one of A or B is non-zero, and so its divisors are always less than or equal to its absolute value. So anyway, it does exist, and we also get some cheap inequalities that we can read off from it, namely, when both A and B are non-zero, all the common divisors have to be less than the absolute value of A and less than the absolute value of B. So A comma B is between 1 and the minimum of those two numbers. When B is 0, then everything is kind of trivial, and you get the following, that the greatest common divisor of A and 0 is the absolute value of A, and that's because everything divides 0, so the greatest common divisor is just the greatest divisor of A, which is the absolute value of A. All right, quick examples. The common divisors of 12 and 8 are, if you make a list of all the divisors of 12 and the divisors of 8, the common divisors will be 1, 2, and 4, up to plus or minus, and so the greatest common divisor is 4. Similarly, you can do another example with 12 and 7 and find that their only common divisors are 1, and therefore the greatest common divisor is 1, and 12 and 7 are relatively prime. All right. This type of calculation by making a list of all the divisors clearly works with any example, but it's also pretty obvious it's a terrible way to do these calculations. So in practice, if you're doing things by hand with reasonable sized numbers, which for me means small numbers, then there's a great theorem that calculates the greatest common divisors in terms of prime factorizations. Now, we can't prove this theorem just yet. We have to prove the fundamental theorem of algebra, which we'll do shortly. And then once you have that theorem, this is so easy, this theorem becomes a homework exercise. So I'll state it now, and you're welcome to use it, but we won't prove it just yet. And as I said, it'll be really relegated to an exercise. Looks like it's homework exercise number 28. All right, let's state this for just positive integers. So start with a and b bigger than 0. And then, as I said, we'll see shortly, you can always factor these uniquely into a product of positive primes. So you write a as a product. Remember that's the Greek letter capital pi, which is like the English P, which stands for product. It's just like the summation notation, except instead of adding things, you multiply. So it's a product of primes pi to the powers ni, and b, similarly, pi to the mi. So the p's, the p sub i's, are distinct positive primes, and these powers are at least 0. Normally, when you write a number as a product of primes uniquely, you want these powers to be at least 1. But in order to make sure we're using the same list of primes here, we'll let ourselves use 0. Then, the greatest common divisor is just the product of over the same primes, where you take the minimum of these exponents at each choice. So this gives, again, for numbers, you can work with your hands, a fast way of calculating greatest common divisor. So here's an example. 12 is 2 squared times 3. That's its product into primes. And is 2 cubed and no copies of 3. So that says the greatest common divisor. You start with 2. It's a minimum of between the number 2 and the number 3 here in those exponents. So that's 2. And then for 3, you grab the minimum of the number 1 and the number 0, which is 0. And then you get 4, just as we had before. All right. There's also an important result called the Euclidean Algorithm. And you can see that also in your homework. This is for computational purposes. It's also straightforward to prove. We won't actually really need this result at all in the text, but if you ever want to compute these on a computer for large numbers, then you can compute them very rapidly. And exercise 20 is the careful statement of the Euclidean algorithm and the outline of its proof. And you should really read it. You should be aware of this result. All right, the result that we are going to use a lot initially is another description of the greatest common divisor. And even though greatest common divisors are all about, products, what's powerful about this is it writes the greatest common divisor as a linear combination, so as a sum. So here's the theorem. Start off with integers that are not both 0. Then the first statement is that you can write the greatest common divisor as a linear combination. So a comma b can be written as ax plus by for some integers x and y. Now the x and y are not unique, and at first blush I suppose this looks like a pretty useless thing, but its importance is hard to overstate. We use it a lot. So mainly the whole point of the theorem is number 1, but I'm going to add a number 2 because maybe once or twice it's useful to know this result as well. So it turns out you can write the greatest common divisor as the minimum of all these linear combinations, at least the combinations that turn out to be at least equal to 1. And in fact, really, that's the whole proof. So the trick of this whole theorem is just to start with this set we wrote down, give it a name, and then follow your nose, and you'll be done in no time. So here we go. So there it is. S is the set of linear combinations of A and B. where the combination is at least 1. First of all, S is not empty. And for instance, you could use x equals to a and y is equal to b. I'll let you check that that will satisfy the requirements. Also, it's clearly bounded below by 1. So it's a non-empty set bounded below, and because it consists of integers, then we get this result that there is a minimal element. We're going to call that minimal element C. And we claim it's going to turn out that, okay, so we have C is the minimum of these linear combinations that are at least 1, and our claim is that C will be our greatest common divisor. If we do that, then we've proved number 1 and 2, of course. So what do we have to prove? First of all, we have to show that C is indeed a common divisor. All right, well, the argument with B is the same as A, so we need to show that C divides A. So, well, this is, I guess, an argument by contradiction. But first of all, let's use the division algorithm. Since we only have one theorem, it's kind of a no-brainer that we'll use it. We'll look at what happens when you try to divide A by C. So the division algorithm lets you write. So A is CQ plus R for some Q and R, some quotient Q, some remainder R. C has to be strictly bigger than the remainder. Now, we're wanting to show, of course, that C divides A. If C does not divide A, then the remainder is 0. I mean, if C divides A, the remainder is 0. But if C doesn't divide A, the remainder has to be at least 1. But if we look at this equation here, this tells us that R is equal to A minus CQ. And now we haven't used the fact that C is in S yet. So that means we can write C as a linear combination. But now we can just gather terms, get all the A's and B's by themselves. So in fact, R is itself a linear combination of A's and B's. But since R is at least 1, coupled with this fact, we see that R actually is an S. But this, then, is a contradiction to this statement up here. That statement says that R is an S, but C was supposed to be the minimum, and yet R is smaller. So that's the contradiction, and as a result, we see that C actually has to divide A. All right, so now we have the fact that C, the minimal element of S, is a common divisor. We still have to show that it is the largest common divisor. Now, oddly enough, to prove this result, we'll end up showing something much stronger and much more useful. What we'll end up showing is that if D is any common divisor, then D actually divides C. So, any common divisor of A and B actually divides C. If we do this, then that'll be sufficient. So D will be less than or equal to C. Don't forget C was positive, so we don't need absolute values. So we get D is less than or equal to C, and therefore it's the largest. All right, so here we go. And once you think to do this, by the way, then there's almost nothing to do. So since D divides A and B, this, of course, says that they divide any linear combination. We're going to use the same combination we did before. That's the combination that made C. So D divides C. That's the end. All right, a corollary of the proof, the result we just showed, in fact, this last part, is the following. Again, for A and B integers, not both 0, and any common divisor of A and B, then in fact D divides the greatest common divisor. I think the first time you see this, it's kind of surprising because initially the greatest common divisor was just the largest on the list, but it turns out it's a multiple of everything on the list. In turn, this allows us to, as a corollary, give an alternate definition for the greatest common divisor, and this is actually the definition that we use when we start generalizing things to different types of algebraic systems later. So again, a and b integers, not both 0, then c is, an integer c is the greatest common divisor if and only if two properties. The first is simply that it's a common divisor. You can't get around that. And the second is the replacement for largest common divisor, and it's this division property from the above corollary. If D is a common divisor, meaning it just divides A and B, then it divides C. All right, so that's it. All right, so that's it for our lecture, but I do want to mention some homework exercises that are very useful to know, and some of them we'll use a lot. They're all supposed to be straightforward, but I want to at least list them here. So let's start with a result from exercise 17. Oops, let's move that down. Exercise 17. Well, this is often for use in with the division algorithm. So let's see. If we have a bunch of integers and we let a be something that comes about when we do the division algorithm, so we write a is equal to bq plus r, a and b not both 0, then turns out we get this. Then if we want to do the greatest common divisor of a and b, it turns out from a you can subtract as many multiples as b as you want, and so a comma b is the same as r comma b. All right, so that's the first exercise to be aware of. Let's see, the next is exercise 18. There are a number of things in here that we use a lot. So the first one is this. Let me, I'm not going to specify all the requirements. Things like a and b are integers and not 0, and c and d is an integer, so you can look in the exercise if it's not clear to you what the technical assumptions are. But anyway, part A says this. If a divides c, b divides d, then ab divides cd. It's super important for part B here to know that just because a divides c, a divides c, and b divides c, that just absolutely does not give you that ab divides c. It's a shame it's not true, but it's just not. You can write down lots of examples. So anyway, however, part C of this says that if you add one more hypothesis, then you do get this result. And the hypothesis you need is that a and b can't have any common factors. Anyway, this proof is fun, and it's one of the typical examples. The main idea of the proof is to use this and write 1 as a combination of a and b. Anyway, so super important result, again in the exercises. And I think that's all we'll state for today. So that's it.